Hey guys, Chill here. Welcome back to Coding Problems with the HackerRank interview preparation kit. Last time we looked at Sherlock's anagram BS, and so I figure we did something with this dictionary hash maps. Let's go back to arrays. Let's check these array boys out again. See what we got here. So let's take a look at this one, the hard array manipulation. So this is actually an interesting one, as the hard challenges usually are. It's interesting, but it's not super hard. I wouldn't consider this one super hard, and the percentage rate reflects that. It's only 54%. The really hard ones are down in like the 30s or the 20s. So yeah, it's a good one. Let's check it out. Let's see what it is. The problem itself is not too difficult to understand. It just requires a little cleverness in order to solve it within the constraints. So what you're given is you're said, okay, you start with a one index arrays of zeros. Array of zeros looks like this, okay? And then you're given a list of operations. For each operation, you add a value to the array elements between the two given indices. So basically, you're given a range, and you're given a value, and you want to add this value to all the elements in this range. So here, if the operation is add 3 to elements 1 to 5, the result is going to be this array here, where 3s have been added to these first 5 positions. And then here, you're going to add 7 to the 4 to 8. So it's going to be 3, 3, 3, then 10, 10, and then 7, 7, 7. And so on and so forth. So you're given a big list of operations, and you have to build them up, and you get this array result. Now, the thing you want to return, where does it say here? Return the maximum value in your array. So after you're done, you find the maximum in this array, and that's your answer. So on the face of things, it's not that complicated. It's just simple. It could be done with simple loops. Only you look at the constraints and you see that, first of all, your n can be 10 to the 7. So your array is going to be like 10 million integers. And your operations, 200,000 operations in the maximum. So 200,000 operations, if each of these operations runs the entire array, like it is possible to do, your result would be, m times n. So you're looking at 10 to the 12 operations, and that's going to time you out. Also, just an array of 10,000 integers might be too large for the maximum. I don't know what the maximum is for this thing. It might be okay, but it's still a very large array. So the naive solution, the naive brute force solution of just having the array and then looping through and performing all the operations naively, it's not going to cut it. It's not going to work. So then the question is, well, what do we do? How do we solve this problem? How do we avoid, that n times m complexity? Well, let's take a look at some stuff here. So we got our array here. It starts off all values 0. And then we add some value to a range. So, imagine this as a graph. This axis is the value. This axis is the index. It's going to look something like this, right? We've added some values to a range. And then let's say we want to add values to a different range. You want to add to this range here. So what we do? Well, add the value like this, and it's now going to look, something like this. And, we'd keep adding values. We'd keep building it up like this. And at the end, we'd have a maximum, and that would be our answer. Now, we look at this, and we see there's some redundant information here. I mean, instead of encoding this as an entire array, all these values, most of the values are going to be the same. The runs in between these changes. The changes happen on our range start and end of our operation. And in between those is mostly just the same value. So instead of encoding it as every value at every index, we could just encode it as runs. Like, for example, this first one here, the value is 0, and it might run on for, 40. And then here, well, this value is going to be, let's say, 10, and it might run on for another 40. And then this one might be 20, and runs on for 40. And this would greatly reduce the amount of data storage that we would need and the amount of processing we'd need to do. Instead of storage being on big order of n, now it's big O basically of m. It's based on how many operations you have, because how many operations you have dictates how many of these transition points you have. So that's a good idea, and we could encode that and run some algorithm on that, but it's not the best idea. But it leads us into the idea that we're thinking. So if we look at this here, we say, okay, when we're starting, our max or our level, let's call this level. Our level is 0. Then at the beginning of a range, level is going to be equal to the k of that range, right? So we hit a range, a start, level goes up. Level stays the same until we hit another start here, the start of this operation for green, and then level will go up again. And then we're going to hit the end of a range, the end of the yellow range, level will go down. Then we hit the beginning of another range, level goes up. We hit the end of the green range, level goes down. And then we hit the end of the red range, level goes down, and we're back to 0. So if we just process these as events, and at every event, we increase the level for a start, and at the end of an event, we decrease the level, we can keep track of the level across all the events, and we can maintain the maximum level that we encountered, and that would be our answer. And now, we don't have to store any of the array here. We don't store anything. We just loop through our events, and the only thing we store is the current level and the current maximum. So now our operations here are going to be on the order of m, right? The number of commands, because every command has two events, a start and an end. Start will increase the level. End of a command range will decrease the level. So that's all we do. We take those commands in and we process them. Now, we have to do it in order. So we have to actually sort the index of each of these events, and then we process them in order. We keep track of the level. So it's not that hard. It's not that difficult. It's not going to be a lot of code. But the trick is to have that paradigm switch in your mind of, instead of looking at it as an array and you're performing operations on the elements of that array, to look at it in terms of events and levels. If you look at it in terms of events and basically the accumulated level up until now that is built up and brought down by different events, then the problem becomes very simple to solve. So that's the trick to this one. How do we solve it? Well, it's not that complicated. So we need our vector of events. So I'm just going to use pair, even though it leads to some, kind of ugly code where it's like .second, .first, but it's very convenient. So we got a pair. Those are our events. So what are these two elements of the pair? Well, the first element is going to be the index of the event. When does it happen in the array? And the second element is going to be the delta change. How much do we add to the current level when we reach this event? Now, since we know how many events we need right up front, we can do a little micro optimization. We can save ourselves a few allocations for dynamic growing. The number of events is just going to be queries dot size times 2, right? Every query or every command will be given an event for increasing the value at the beginning of the range, and then another event for decreasing it at the end of the range. Not decreasing the value, but increasing the level, right? So now that we have that, we're going to loop through all of our queries, and for each of these, we are going to put 2 events into our event vector. Now, the queries, every query is a vector of 3 integers. So the first integer is the start of the range, the second integer is the end of the range, and then the third integer is the value, the amount to add over that range. So we're going to do events dot in place back, and the first one is going to be the index. That's Q0, that thing, and then the value, which is Q2, the third element there. We'll use this style here. Not my usual chili style, but it matches all the rest of the code in this thing, I guess. And then events dot in place back. Oh yeah, we got that. Sweet. We got our code completion. And the index here, the event index, is going to be Q1. Note that this is different than the array index, but array index doesn't matter. We're not storing an array, right? So it doesn't actually matter if it's 0 indexed or 1 indexed. All that matters is the order of the events. And now the second event, the value of that one is going to be negative of the first event, right? Because the first event adds to the level, and then when the range is over, the level is going to go back to where it was before. So one event to add, another event to bring it back down. There you go. You've got your events there. Now we have to go through the events in order so that we build up the proper timeline. We build up the levels. So we have to sort our events. One of the beauties of using pair is that it already implements the comparison operator. So we don't have to worry about that. We can just sort our poopy. Now, once we have the events and they're in the correct order, all we got to do is loop through those and build up the level. So we're going to do long max is equal to 0, and long current also equal to 0. We could do this with std algorithm. It would be a little slower. It'd still be the same time complexity, but let's do it the way that's going to be slightly faster. Maybe around, in the best case, maybe around twice as fast. Int last index is equal to 0. So basically what we're going to be doing is we're going to be looping over all the events. So we can just use your standard range-based for loop here. And for every event, we're going to add the value to the running total. And then we're going to see if that is greater than the maximum that we've seen so far. And if so, we're going to update the maximum. Now, the only problem here is that you could have multiple events happening at the same time index. So imagine you have, 2 plus events and a minus event happening at this time index. Well, if you add the first plus event, and then you add the second plus event, and then you subtract the minus event, this is going to be the level at this time index. However, if you were to just process the events individually without the context of them happening at the same time, what should happen is you would detect this as your maximum, when really, at this time point, this should be your maximum. So what we want to do here is we want to basically detect the case of where multiple events are happening at the same time. So we use this last index to make sure that the indexes, to detect if the index has changed, and only update the maximum if the index has been updated. Now, there's a reason why this might not be necessary, and I'm going to look at it in a second. But first, let's just put it in there. So what we're going to do is if e.first, which is the time point or the index, if that's not equal to the last index, that means that this event is a different time than the last event. So in that case, we can update the maximum, which is equal to std max. And I'm going to use std here because we've used max for this variable here. So that just, disambiguates it. Is that a word? Disambiguate? Sure. I'm going to say it's a word. So we update the maximum in that case. And then we also update last index. This is now the last index that we've seen, e.first. And then regardless of whether we're going to be updating the maximum or not, we want to always add the value of this event, e.second, to the current running total. And then at the very end, when we reach the end of the array, we're going to make sure, we're going to do another check here, std max of the maximum and the current running total, because there might have been a running total here that wasn't registered because we exited the loop without hitting this. So we do this, and that should be our value. And that's it. And not a lot of code. Let's see if I made any syntax errors. Probably did. Nope, didn't, but I'm getting the wrong answer here. So let's look again at our algorithm here. Did we miss something? We got our pairs of events. We are reserving the size. We are emplacing into there. Q of 0, Q of 1, those are the two indices, and these are the values. Symmetrical, adding and subtracting. Sort, that seems good. Wait a minute. Here, this subtraction event is happening on the, here. It's happening on this index, the second index, subtraction event. But that's not correct, right? Because these are inclusive. First and the last range, they're both inclusive, which is different than the standard in C++, right? In C++, you have your first iterator points to the first element. The last iterator points to one past the last element. And that makes things very nice for loops. It makes your code cleaner. But this coding problem isn't quite so nice. It includes the last element here. So that's a little disconnect from my code. What I should do is I should add 1. The subtraction should happen 1 after the last index. Let's run that. Okay, that seems good. And then if I submit the code, there you go. We've solved the problem. Beautiful. Congratulations. Now, one last thing that I just wanted to talk about here. We did this last index thing here to basically detect whether an event is at a new time point or whether multiple events are happening at the same time point, and we only update the max when we hit a new time point. And the reason for this was, like I shown you here, if you do your adds first and your subtraction last, you're going to end up with an intermediate maximum that is greater than the real maximum at that time point, and that will give you bad results. But here's the thing. When you sort a vector of pairs, it is going to sort first by the first element order. But if the first elements are the same, if the time point is the same, is then going to sort by value, which is going to put the negatives before the positives. So if you do this in order, your subtractions will happen before your additions. And in that case, we should be good to simplify this. So the simplification would be, we don't need the last index here. We don't have to test to see if the index has changed. So we can just do this. We perform the addition, and then we capture the maximum. So because the subtractions will happen first, the maximum will never be greater than the true maximum at any time point. And so here then we can just return max, because now we're capturing the maximum at every iteration. Let's try it. Let's make sure we don't have any bad syntax from our code editing here. It works fine. Let's run it and see if it actually works. My theory is that this should work fine, but I could be wrong. No, it works fine. So yeah, we could simplify that code. The reason is because we've actually sorted first by this component of the pair and then by this component. That allows us to simplify this, and it's very nice, very simple. So what's the time complexity of this operation? Well, you might say we just scan over these events. So the time complexity is, big O of M, or 2M if you like, because, there's 2 events for every command. But you have to take into consideration one thing. What is that thing? You have to sort your events, and sorting is n log n. So that means our time complexity for this problem is actually m log m. That's what you're looking at. You're looking at an m log m, or if you want to say 2m log m, that's fine. But we don't consider, those multiplicative constants in complexity analysis typically. So this is m log m, which is pretty good. It's obviously much better than m times n, because n can be a very big number, much larger than m. And there you have it. And I like this problem because, I like the paradigm shift in thought that you have to make, moving from just, a simple array of numbers to this, array of events and then running over those events, scanning through them, and doing the stuff. Like I said before, you could actually simplify this code at the cost of a little more work the CPU has to do. Instead of doing this raw loop here, you could do it with STID algorithm. You could do a partial sum, which does that running total of the events. You could do a partial sum followed by a call to STID max element, but that would have to run over the container twice instead of once, so it would be slower. And this code isn't that complicated, so I wouldn't bother doing it just to show off the STID algorithm's flair. But just to note that you could replace this simple loop with calls to STID algorithm if you were so inclined. But that's it. That is going to do it for this episode. Hope you enjoyed it. Hope you learned something. If you did, please click the like button. Helps a lot. And I will see you soon with some more coding problems.